It's spooky season, which means three things: warm jumpers, pumpkin spice, and the terrifying treachery of the Simpsons treehouse of horrors. Now, we know that Bart's pretty good at telling scary stories, but is he any good at trick-or-treating? Let's use data science to find out. So the first and hardest step in any data science project is not actually doing the data science or the modeling or any of that kind of stuff. It's actually getting the data, but I was lucky this time because I had an idea. My favourite Mum Doesn't Want You Playing Violet Games game, The Simpsons Hit and Run. But while the game is iconic and the cars break down in such a satisfying way, when I looked at the maps, I actually found them to be quite abstract and simplistic and realised that this was not going to be the easy win that I thought it was going to be. I considered a detour to Pawnee, and believe me, I really wanted to get my nope on, but it turns out the Parks and Rec nerds aren't the kind of nerds to make really detailed maps of the town, but you Simpsons fans, you are built differently, and so on Reddit I found this work of art, a beautifully created map of Springfield that labels every single location. This is where the project felt suspiciously easy, but don't worry, I was about to encounter my first trick because I had to manually go through the entire image by hand to mark the character locations. And you might be thinking here, why didn't you just ask AI to do it? I mean, that's literally the sort of thing they're good at. And I did, and they were rubbish. So it was back to me. I spent I don't want to know how ridiculously long manually marking the location of every single character in GIMP image editor, and when I sat back triumphantly like, I've done this is beautiful, I realised my next problem. Python can't read stuff from GIMP image editor, and in order to do data science with it, I need to get it into a vector face format instead. So I took a crash course in Inkscape and did the whole thing all over again, and I'm definitely not a graphic artist now by any stretch of the imagination, but I did have something that the computer could finally understand. See, I'm resourceful. I did get my nope on after all, but unfortunately, there's a few more problems. Because I was tens of hours into this project, proudly showing anyone who would give me the time of day a map with the Simpsons characters all plotted in there with their locations connected to each other, when I realised Most Tavern is closed, it failed its health inspection, he's not giving out candy this year, and I'm not going to find out why, so let's move on. So with 31 Simpsons characters plotted on the map, I was ready to begin my real quest, because Halloween isn't just finding the shortest distance between two paths. No, the true meaning of Halloween is eating so many sweets that you throw up while avoiding some pitfalls along the way. I've been boxed in by a load of sound panels that haven't gone on the wall yet, but at least a Halloween colour. So plotting 31 Simpsons characters on a map is all well and good, but if we actually want something we can work with, we need to be able to join them up. Like this. What this means is every character has a way to get to every other character, and no one's hanging out on their own except for Mo, but we just ignore him. And this is exactly what we need, a way to get around to all the houses that have candy. But in reality, this simple starting point is unrealistic. Other than a basic check that we can get between everyone, this doesn't really tell us anything. Let's do better. One thing we can do is we can add weights to the paths. So distances that are further have a much thicker line connecting them. And yes, I know you can see visually that Mr. Burns doesn't live anywhere near the plebeians, but the computer doesn't know that. It needs paths to get around. I did notice when I zoomed in a little closer that something a little bit weird was going on around Evergreen Terrace. I mean, surely Ned next door lives closer than Millhouse over the road, but maybe some of the changes we're about to make are going to sort this out, so we're going to come back to this problem in a little bit. So this gets us closer to something we can work with. I mean, it certainly symbolises what we want to do, but we do have a problem because these paths are completely direct, ignoring anything in the way, just go straight from A to B. And last time I checked, Bart can't ollie over buildings. So if we think about real world maps, when you ask Google for directions, it doesn't just draw you a straight line. It actually tells you where to go. It gives you the left and the right turns that you need to take and the paths you need to do to get there. And it also gives you multiple options. If you're looking to travel down Abbey Road, but you know there's going to be a massive queue of people on the crossing taking pictures, then maybe you'll go down Grove End Road or Hamilton Terrace instead. Maps suggest that for you. Similarly, when we think of lines connecting our Simpsons graph, we can't just draw one path from one character to the other. There are multiple options. So we need to actually take into account every single intersection and every single road segment. And this is where things start to get a little bit interesting, because for the crow's fly route, we've been taking the Euclidean distance. So that's the square root of the change of x squared plus the change of y squared in order to calculate our distances. But the real world doesn't work like that. Instead, we need to start using the Manhattan distances, literally calculating the distances like on the grids of Manhattan. That way we can create a graph that looks like the crow's flies version, but actually uses Manhattan distances. This makes everything much more simple, both visually and mathematically, but keeps the integrity of the original paths intact. The only problem is building it. Because in order to make this happen, we actually need to build a more complex graph first, one that takes into account every single intersection on every single road. And let me tell you, this was a nightmare, because with the tens to hundreds of roads, the problem blows up exponentially. And well, if you want to scare this Halloween, take a look at this graph. When you see this, you understand immediately one of the biggest challenges in data science. Sometimes, in order to solve something, you need to simplify it first. By the way, if messy data like this gives you a jump scare, join the Evil Lair to find out about the teaching and the tooling that we're creating to make data science a whole lot less scary. Details in the description. So how do we get from this jump scare to something manageable? Well, if we know the path from Cletus to Mr. Burns, then we could just take out all the intermediate intersections and road, use the Manhattan distance, and draw a straight line there. But we have a problem that we saw earlier, and that's that there's multiple paths to get between Cletus and Mr. Burns. Some of them are perfectly reasonable, but it's also very possible for Bart to just wander around every single road in the entirety of Springfield before he gets there. And despite the fact that it might use more calories than he'd gain from wolfing down that candy, it is a valid path. In reality, if we want Bart to optimize his trick-or-treating route, then we need to cut down on the amount of time that Bart spends wandering the streets of Springfield. And in order to do this, we need to find the shortest paths. Now, this sounds complicated, and it's going to sound even worse when I tell you this uses something called Dijkstra's algorithm, but actually we're not going to deep dive into how that works today. That's a topic for another video. There are efficient packages that you can get to just implement it for you. So what you need to know for today is that it's an algorithm that finds the shortest path between 2 points. By using this for every pair of characters, I can build a simplified graph that just shows me all the shortest paths between the characters as given by their Manhattan distances. So like in most of our data science videos, a huge amount of time has been spent getting the data into a usable and clean form, and now we can actually start modeling. Don't ever tell us that we hide the glamour of data science. So how do we get to the exciting part of actually trick-or-treating? Well, in order to do this, we need to introduce the concept of rewards and penalties. Wait, isn't that just basically what trick-or-treating is anyway? So obviously the treats are rewards, and we want Bart to maximise his candy collecting. So for those characters that are more likely to give out treats, we want to give them a higher reward score. The other characters though, some of them hate children in general and Bart in specific. I mean, Principal Skinner is not giving that boy chocolate, and Sideshow Bob might just steal all his candy. Or worse. So I asked the Simpsons enthusiast to score all the characters for me, and he gave me justifications as to why he thought each character would give out each amount of candy. So for example, Professor Frink, he's probably got some weird experimental stuff and he needs people to try it, so he's going to be giving that stuff out. Krusty, he has a soft spot for Bart as well, we know that, so both of those give out a 7. Sideshow Bob though, he's a -20. Do not go near Sideshow Bob. What made it hilarious actually is when I ran the algorithm for the first time, and all of my first attempts came out with Bart just casually swinging by the prison because the distance saved was worth the penalty of losing all of his candy. And so I had to scale the weight a few times and work with that a little bit, so finally Bart was disincentivized to not go and say hi to Sideshow Bob. But trick-or-treating isn't just about candy, it's about getting home before bedtime, because otherwise this would be a really boring video where Bart just goes to all the places that are positive. So we have to set a time limit. And given sunset hours and the fact that Bart is a 10-year-old boy who does need to go to bed at some point, 2 hours sounds about right. With this setup, I can work out the optimal route using an orienteering algorithm. And I'm not going to go into the details of this because that's a whole other video, and there are packages that you can use to start using it straight away. But what is really important is to understand the difference between this and Dijkstra's algorithm. Because Dijkstra's algorithm is about finding the shortest path between 2 points. The orienteering algorithm is about maximizing the rewards along the path that we take within a set time limit. One quick aside, the orienteering algorithm is set up to measure everything within a time limit, but my routes are all given a distance, and because we know speed, distance and time are basically equivalent, so I converted my times to all be distances because that meant I didn't have to remake my graph and just make the code a little bit simpler. As you can see, it gives us a pretty reasonable route around the neighborhood. It certainly avoids Sideshow Bob, which is really important, but there are still a couple of things niggling at me. Like some of the problems from earlier we haven't quite resolved, and what about the time that Bart spends chatting? Remember that weird distance discrepancy between Ned and Millhouse, where it was 3 times as long to get to Flanders as it was to get to Millhouse? Well, I think it's time to solve that, and in order to do so, I am going to get to play The Simpsons Hit and Run after all. I made that look so awkward. So I'm gonna set a timer and see how quickly I can run from Homer's house to Ned's house, okay? So I've got my timer here. Ready? 3, 2, 1, go, 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 Homer, go, 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 go. Ah, do we have to run over the path? We can go over the drive. Ooh. Quick, 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 quick. Run, 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 run. Run, run, run. There. Okay, when I rehearsed this, I did it quicker in 17 seconds, but we got 22 seconds this time, which is kind of close enough. Now, this is faster than a walking speed because Homer was running, but I mean, come on, it's Homer. He's not running much faster than Bart's normal walk. This also enables us to create something called a Springfield unit, and we don't have to worry too much about what this means in practice, just that it's a way to standardize the distances in a way that makes sense for Springfield. One final thing that I can add is a time penalty for visiting a house. Bart's really well known in Springfield, both famously and infamously, so he's going to spend time chatting. So let's add 5 minutes, or equivalently 5 minutes worth of distance, to each of the characters to take into account the time that Bart spends receiving lectures. With all this in place, we are ready for our final reveal. So here on the left-hand side is the before path, before we took into account Bart's walking speed and time spent chatting, and now I'm going to reveal to you the new path on the right in 3, 2, 1, boom! All that time spent running complex models, calculating distances, using the Simpsons hit and run to work out his walking speed. I mean, all of that, and he just takes the same route that he would take anyway, just going around the local neighborhood and hitting all the candy-rich houses. Guess my Halloween's ended with a trick. So why do we do all this? Well, it's not just an excuse for me to play Simpsons Hit and Run, and it's not just a reason to make a tenuous link to Halloween for this video. No, we did this because this kind of problem comes up all the time in the world of data science. For example, think about oil shipping. Much oil is extracted from the Middle East, but actually gets refined in the US. And if we just took the shortest route to get there, then the oil tankers would all go through the Suez Canal. But there's a problem. There are large fees to go through the Suez Canal, which acts like a penalty in the optimization. Instead, oil tankers from the Middle East to the US go all the way around the Cape of Africa. It's a much longer journey, but it's much more cost effective. And this is the kind of complex problem that we're solving at EvilWorks, making it much easier to do the actual data science so that you don't have to go through the absolute nightmare of visualization that I had to in order to get on with the stuff you actually want to do, which is the modeling and the optimization. But not enough of a nightmare that I wouldn't do it again if someone made me the math porny. So if you are a Parks and Rec nerd like I am, then let me know in the comments below, or drop into our community of data scientists, the Evil Lair. The details are in the description. Please like and subscribe, and tell me, who do you think would give Bart the most candy?